Hi, my name is Garen Porter, and our Capstone project is creating a pyranometer, which is IoT solar radiation sensor. Our client is Dr. Chet Udell, who's part of the Opens lab here at OSU. My two group members are Brooke, Weir, and Alex Tovar. So in this presentation, we're going to be going over the core requirements of our project. First of which is integrating all of our software into Loom, which is a software package written by the Opens lab for IoT devices. So we have three different sensors we're using, the TMP-007, which is a thermopile, the SI-1145, which is a UV sensor, and the TSL-2591, which is a lux sensor. So all of these have been integrated into Loom. So all the sensors need to be separately configurable in Loom, which means we need to be able to specify how they package their data, what they measure, any calculations on their measurements. So we need to be able to separately configure the settings for each of the sensors, which we've enabled in our software. So all the sensors need to be operable with a multiplexer. So the multiplexer allows us to use multiple I2C sensors without use of a breadboard, which is crucial for our project in order to keep it small. So all these sensors need to work with the multiplexer so we can get all the data we need. So the data needs to be well formatted, so it's easy to read by users. The data is eventually uploaded to a Google Sheet, and so users need to be able to discern what the data is from looking at the spreadsheet. So we're using Pushing Box to upload our data to the spreadsheet. So the Pushing Box needs to be properly configured to do so, and it has been. So we have two devices. We have the hub and the node. The hub receives data and pushes up to the Google Sheet, and the node is the actual pyranometer. It measures the data, calculates the watts per meter squared of the sun, packages the data, and sends it off. So these two devices need to communicate with each other using LoRa and be able to work consistently. So all the data is going to be stored on an SD card, just in case data is lost over the wireless transmission. So all the data will be saved somewhere. So we can step over here and look at the code real quick. First, we have the main loop on the node. So it's pretty simple. It's just going to measure all the sensor data, package it up into a bundle, send the bundle over LoRa, and then it's going to save all the data to an SD card for later use. It's just going to do that over and over again until the battery dies. So here we have a config file. And what we're doing here is we specify what dependencies need to be included, and also like what type of device this is. So we specify that this is a node in the case of LoRa, and then we enable LoRa and disable things like Wi-Fi and Ethernet. And then the other thing we do, perhaps the most important, is we specify what sensors we're using. So Opens Lab has a bunch of sensors, as you can see, but we don't need all those dependencies for the sensors included. So we're only going to enable the three sensors we need. And what that's going to do is it's just going to include those libraries onto the microcontroller. So it's going to save a lot of space. And so we can take a look here at the multiplexer code, and the code itself is pretty long and complex. But basically what it's doing is it's looking for the specific addresses of these sensors. So I2C sensors are given a specific address by Adafruit, which is the manufacturer of the sensors. And so we specify those here, and this tells the multiplexer exactly what to look for, where to read from. And so we take a look over here at the thermopile code, and the code for the three sensors all looks very similar, where we have a state, and then a setup function, and then we have a package function. So setup, package, the state. So they all have the same format. So the state contains the sensor readings. So we have the voltage, object temperature, dye temperature, and then the calculation that we do later on. So we call this begin function, which all I2C sensors have, sets up the sensor, gets it ready to read data, and then assuming that passes, it moves on. And here's where we package up the sensor data. A lot of it's commented out because we don't actually want to send the volt information, the object temperature information, dye temperature information over LoRa because it's going to clutter our data and it's going to look bad in the spreadsheet. So we actually only want the total watts per meter squared. So we're just going to bundle that up. But we see a scenario where future users of the pyranometer may actually want this data. So this is especially evident in the light sensor, where we don't actually report the flux of IR visible in full, but users can be free to get those if they want it. So finally down here is where we actually do the measuring. So we're going to read the voltage, object temperature, dye temperature, convert it to kelvins, wait 4 seconds, read it again. This helps us get a change in temperature over time. And then we're going to do some fancy math to finally get total watts over meter squared of the sun. And we'll go over the math a little more detail later on. So yeah, all the sensor files have the same format. And specifically with the UV sensor and the lux sensor, rather than do a bunch of math, we're just going to multiply one value by a factor to get the watts over meter squared. So in this case, we multiply the UV index by 0.025, and then in the case of the lux sensor, we're just multiplying each of the different fluxes by 0.0079. So finally, we jump over here to the hub side of things. So the hub is really simple. It just receives a bundle, checks if it's empty. If it's not empty, pushes it to the Google spreadsheet. That's pretty much it. Most of the time, it's receiving empty bundles. But every once in a while, it's going to get an actual bundle from the node, and it recognizes that and pushes data up. And so in the config file, 0 sensors are enabled, so it has very little dependencies included. It's set to be a LoRa hub. And finally, we have the pushing box configuration here. So the spreadsheet ID lets it know what spreadsheet to upload it to. This is part of the URL in the Google Drive spreadsheet. The device ID is a number given to us by pushing box when we set up the scenario. And then the tab ID is the actual tab in the spreadsheet that's going to use. If Pyro 3 doesn't exist, it's going to create a new tab called Pyro 3. And then the important thing to note down here is the delay. So we wait. So what this says is only push every 2 minutes or 120 seconds. The pushing box only allows 1,000 pushes a day, which is roughly once every 2 minutes. So, alright, so we go a little more deep into the math. So, what you start with the thermopile, the most complicated. So we're using a pretty basic physics principle of conservation of energy, where the change in energy in a system is equal to the energy in minus the energy out. So the change in energy is related to the change in heat in a system, and that equation is going to be the mass of an object times the specific heat of an object times the change in temperature of the object over time. In our case, the time is 4 seconds. And this object I'm referring to is a black body dome, and we have a picture here real quick, which is this guy right here. So this black object heats up, and then the thermopile sits under it and measures it. And so the second half of this equation is the energy out, which is Stefan Boltzmann's law of black body radiation. So we're using the emissivity of the black body times Stefan Boltzmann's constant times the final heat of the object. So we add that to the energy to get total energy in, which is watts over meter squared. Now on the right, we have translating flux data into watt meter squared. So we have this rather complicated integral here that we can't really implement on the microcontroller. And so we were given a factor to multiply flux by Dr. Chad Higgins, who's smart in the ways of physics. So we're able to multiply our flux values for IR and visible by 0.0079 to get an approximation of the watts per meter squared. And for the UV sensor, we're measuring UV index, and there's actually a direct translation from UV index to watts per meter squared, and that's to multiply the UV index by 0.025. And so all this allows us to not only report the total watts per meter squared that the pyrometer is receiving, but also report the individual watts per meter squared values of the different wavelengths of the light spectrum. So we get the UV, the IR, the visible, and then all of them together. And so a third requirement is the open source aspect of the project, which is the really big aspect of the project, and it's really what Opens Lab is all about. So all of our codes will be freely available on GitHub, as well as the CAD files used to print the structure. And of course, we're going to have complete instructions on what materials to buy, how much it's going to cost, how to assemble everything, and then how to work everything. So we can step over here to the GitHub real quick. We have the CAD folder, which hosts the various parts that are required to put the whole thing together. So users should be able to download these and then use their preferred 3D printer to print them out. So in the Loom folder, we have our code. So here we have the node side. So users should be able to flash the microcontroller that goes inside the pyrometer with this code, and then flash the data hub with this code, and then they should just work. And then finally, we have instructions on how to do all this. So how to flash the different feathers, the hub and the node, how to actually print everything and put it all together, and then buying all the parts and how much they're going to cost. And this is a work in progress. We haven't specified how to actually operate everything. We're going to have a section on, if you have a problem with this, how to fix it, that type of thing. So those will definitely all be done by Expo. And so now I'm going to hand it over to Alex, who's going to go over the housing structure, the materials, and weatherproofing.
Low-cost materials is one requirement that our client wanted us to achieve. We wanted to make the pyranometer using cheap materials to bring the total cost of the sensor down. The solution was 3D printing the structure and the blackbody dome. PLA plastic was used for the blackbody dome. The blackbody dome needs to be able to absorb and emit heat. The effectiveness of this is called the emissivity level. PLA had a higher level than ABS, so we wanted to go with PLA plastic. The amount of heat is important so the thermopile that's under the dome can precisely read the heat coming off of it. The housing structure itself is printed using ABS plastic. This plastic is strong and durable, making it ideal for the housing structure. The sensors are covered with some clear materials. These materials are cheap and easy to get. They can be found on Amazon or in craft stores. The thermopile uses clear acrylic domes. They are cheap and durable plastic. The flat cover is a piece of glass, and glass is used because it can allow UV better than other materials. This covers the lux sensor. Overall, these materials can be easily obtained, and it lowers the total cost of the pyranometer. The next requirement after the housing was completed is to make sure that it can survive in the environment. The main issue is making the pyranometer waterproof. There are two things that we did to waterproof the pyranometer. The first was to coat the circuits themselves using silicone modified conformal coating. Brushing this on top of the circuits provides a layer of silicone protection from water. When brushing, we had to make sure to not get it on certain areas like the sensor on the chip because that could affect the readings. This method is used on the possibility that some water may leak into the structure. The next method is to waterproof the outside structure. The Opens lab has this material called XTC 3D, which is a brand that makes protective coatings for 3D printed materials. There are two liquids available that are mixed in a 2-to-1 ratio to create a layer of resin on top of the 3D printed parts. Brushing this over our structure will add strength and another layer of protection from water. This should help it survive in wet conditions. The double domes is used to prevent any external interaction from the environment to mess with thermal power readings. This includes wind affecting the amount of heat coming from the clear dome. Overall, we'll perform some tests to make sure that the pyranometer can survive weather conditions and other events.
So one of the requirements for this project is that the data will be able to be transmitted wirelessly, and the way that we chose to do that is through LoRa. And LoRa stands for long range radio transmission, and some of the Feather M0s are a Feather M0 LoRa, which means they have a little chip where you can plug in an antenna and transmit information through radio waves. So what that looks like is our sensor used to just have a Feather M0 Wi-Fi. Now it has a Feather M0 LoRa, which is connected to the multiplexer and then to the ADA logger, and then the multiplexer on top, and the sensors are plugged into the multiplexer. So the sensor, which here for the data transmission purposes we'll call the node will measure data and bundle it and send it to the hub. And the hub is another Feather M0 LoRa connected to a feather wing, which is basically just a board that has an Ethernet connection. And once the hub receives the bundle from the node, it will take it and upload it to a Google spreadsheet via pushing box, which just formats a HTTPS request to actually push data. So this way we can get the data, and we only need Ethernet. The range of the radio waves is pretty far and should be able to transmit through trees, which is important to our project. And currently the spreadsheet has a column for like the voltage of the battery of the Feather, or of the sensors, visible light, IR, visible plus IR, and lastly the most important data point, which is watts per meter squared. And this might change as we format it to make it better for human eyes, but this is how the spreadsheet is set up currently. So here we have this little video. It will take a little bit to load, but you can see the data coming in. As data points, there's a limit to how many uploads you can make via pushing box in a day. So it is a little bit slower than how we're sensing data, but it should be enough data that researchers can get the information that they need. So along with data transmission and making sure that's wireless, another requirement was to have valid data. So this is the part of the project that has been one of the bigger problems this term. It turns out that if you need to use equipment to test your sensor, it's kind of hard to convince people to give you their equipment to test them. And when the equipment is given to you, they might not have the time to show you how to use it. And for those reasons, our data is pretty much untested. So here you can see what watts per meters we're getting now. There are several ways that we will test our sensor when we have the equipment to do so. One of those is the silicon pyranometer, which we had to send to the manufacturer to recalibrate it, which takes a few weeks. Once it comes back, it reports watts per meter squared, and we'll be able to compare them and see and use it to make sure our data gets better. And the main way that we'll do that is by tweaking our equations. Earlier in the presentation, we showed you the equations. There's a lot of variables in there, and a lot of those values were an educated guess, and tweaking those values would help get our better data. We also have to test our thermopile. It was suggested by our client, Chet Odell, that an IR thermometer be used to test it and make sure that it's getting the right temperature. Both of them, you just point at an object and it should tell you the temperature of the object, and having that information will help validate our data. And that is something that we're kind of waiting on equipment to do, and it should be an ongoing process, but for Expo, it should be ready to be pretty valid data.
So in conclusion, we've inputted all the core requirements for the pyrometer. We have a few bugs, and then we're waiting to verify all of our sensor data. So thank you for listening, and we hope to show you a completely finished product at Expo.